In the last video, we introduced the idea of radicals, their stability, and typical chain mechanisms of radical reactions. In this video, we're going to continue talking about radical reactions in a more general sense, the halogenation of alkanes, and we're going to look at the rates depending on different halogens, fluorine, chlorine, bromine, and iodine. We'll look at the selectivity of the different halogens for different CH bonds, and then the stereochemistry of halogenation, radical halogenation reactions. Okay, so before we look at the rate, let's first talk about the thermodynamics of these kinds of radical halogenation reactions. In the last video, we looked at the chlorination of methane. Let's look at halogenation in general. So if we look at bond dissociation energies, this can give us an idea of how exothermic or endothermic a reaction is, right? So, for example, let's look at methane, right? So if we fluorinate methane, we're going to be breaking a CH bond, and we're going to be breaking a fluorine-fluorine bond. So that we have to put in energy to break those bonds. And the products, we're forming a CF bond, and we're forming an HF bond. And so to break a CH bond, turns out that takes 435. It's right here, 435 kilojoules of energy to break a CH bond. So that's plus 435. To break a fluorine-fluorine bond is plus 159. That's a weak bond. To form a CF bond releases 456 kilojoules. So now we have minus 456 because we released that energy. And to form an HF bond releases a lot of energy, minus 569. So what I'm doing is I'm saying anytime you break a bond, you have to put in energy, right, to break the bond. When you form a bond, you release energy. So I'm going to say that's negative. So if we look at 435 and 159, that's going to be plus 594. So this is the reaction, this is the energy in. How much energy did we release? Well, we released 456 and 569, which is minus 1023. So we got way more energy out than we put in, right? So the net result is that we get a huge release of energy. This is a violently exothermic reaction. And so what we're going to say in terms of fluorination, while it's extremely exothermic and favorable, we're going to say because it's so violent, this is usually not of any practical value. So fluorination we're going to ignore. We're going to focus for the most part on chlorination and bromination. These are also exothermic reactions, and that's mostly a result of the fact that we're breaking these weak chlorine-chlorine bonds or weak bromine-bromine bonds, and we're forming. So, for example, breaking a chlorine-chlorine bond requires this 243 kilojoules of energy, but you release way more energy upon forming an HCl bond. You release more energy in an HBr bond than you do by breaking the Br bond. The problem is that for iodination, the carbon-iodine bond is very weak. The HI bond is very weak. So the net result here actually is that iodination is endothermic, and for that reason, it's not favorable. So we don't usually observe radical iodination reactions, so we're also going to ignore that possibility. So the only useful halogenation reactions are going to be chlorination and bromination. So let's focus on those. Okay, so if we look at the two propagation steps in a radical halogenation step, remember the first step is going to be CH abstraction by a halogen. And then the second step is going to be halogenation to form a CX bond, right? So notice that for chlorination, both steps are exothermic, But for bromination, that CH abstraction, that first step is actually endothermic, but luckily the net result of the entire reaction, because how exothermic the second step is, the net result is that bromination is slightly exothermic. It just has a very endothermic initial step. So what does that mean? Remember that the activation energy of the slowest step determines the overall rate of the reaction. So what this tells us is that chlorination is going to be fast. The overall rate of chlorination will be very fast. The overall rate of bromination will be relatively slow. Okay, so how does that relate to the selectivity, right? So now let's look at, instead of methane, let's look at the chlorination of propane, for example. Now we can form two different products, right? We have a secondary CH bond, and we have lots of primary CH bonds. So if we remove one of these hydrogens or we remove one of these hydrogens, we'll get the same product, which is just 1-chloropropane. Notice that chlorination is slightly selective for secondary chlorination over primary. Hopefully that makes sense, right, based on what we know about the strength of different CH bonds. This CH bond is weaker. This CH bond is stronger. So it's more likely that the weaker CH bond will break to form the more stable secondary radical, which will then undergo chlorination. So that's why we get a slight excess in the chlorination. But the problem is, since chlorination is very strongly exothermic and fast, we lose some selectivity, so it's only slightly selective. Whereas for bromination, since bromine is a less reactive, it's a slower reaction, we get much better selectivity for secondary over primary. So both reactions proceed by a radical chain mechanism, but bromination is much, much more selective for secondary over primary hydrogens, and that has to do with the reduced reactivity. Let's look at why in a little bit more depth. So if we're just looking at that first hydrogen abstraction step, this is the rate determining step, this is the slow step, right? Chlorine radical is much higher in energy, so this is more reactive. So it's higher in energy compared to the bromine radical, right? So that means that the activation energy is smaller, which means that the difference in the transition states that lead to a primary, secondary, or tertiary radical are very small differences. So that means that the rate at which you form primary, secondary, or tertiary radicals will be pretty similar, right? Whereas look at the difference between the transition state energies between tertiary and secondary, secondary and primary, right? There's a big activation energy difference between forming a tertiary radical and forming a secondary radical. So this tertiary radical is going to form much faster than the secondary radical, and so that's why we'll get much better selectivity. The faster that you form one product, the more selective that particular reaction is going to be. Okay, so practically speaking, this allows us to predict the major product of bromination. So we're going to assume bromine is much more selective for tertiary over secondary, and secondary is much, much more selective over primary. So if we monohalogenate this molecule, then the first thing that you want to do is identify all the different kinds of hydrogens, right? You have primary, tertiary, secondary, there's no hydrogens here, and that's primary. So we only have one tertiary CH bond. Bromine is much, much, much more selective for tertiary than any other kind of CH bond. So the product of this halogenation would be to replace the CH bond with a bromine. So this would be the major product and pretty much the only product observed. Just to reiterate that, now if you have a choice between tertiary and primary, tertiary much, much, much faster outcompetes primary, so we only get one product from this reaction, whereas even though the chlorine is more selective for tertiary over primary, we get a mixture. So at the end of the day, we'll say chlorine and fluorine will form mixtures. We can ignore fluorine because it's too reactive. Bromine is very selective, so we're always going to predict that there's a single product from tertiary over primary. Bromine reacts 1,600 times faster with tertiary versus primary and 82 times faster secondary over primary. So there's a much more selectivity in bromination than there is in chlorination or fluorination. Okay, so last thing I want to talk about is stereochemistry, and we have to go back to radical structure. Remember, we said radicals are flat, just like carbocations. So think back to the SN1 reaction. If you have a flat intermediate, that flat intermediate can undergo reaction from either face at equal rates. So if we're forming a new stereocenter, like we are if we abstract this CH bond, we're going to replace it with a chlorine. That's a new stereocenter. This is not. So we should get a racemic mixture here, as we'll see on the next slide. So chlorination is going to give a mixture of products here, where we're going to get a racemic mixture of the R and the S stereo isomers, and also this product. Since radicals are flat, they're not chiral. They can get chlorinated from either face, and you're going to form an equal mixture of both stereocenters. One thing that's slightly more confusing, though, is what if we undergo radical reaction at a stereocenter? So for example, let's look at this molecule, right? If we're looking at all the different kinds of CH bonds, we have primary, secondary, tertiary, primary, secondary, secondary, primary. So this hydrogen is the one that's going to be replaced with a bromine. So this product makes sense. Where would this product come from? Let's think about this for a second. Remember, the first step in a radical halogenation reaction is initiation. We form a bromine radical, and that bromine radical is going to abstract that hydrogen to form HBr and the most stable tertiary radical. But now we lost that stereochemistry because this thing is flat and achiral. And so when this undergoes reaction with bromine, that new carbon-bromine bond is equally likely to form from the top face of that radical or from the bottom face of that radical, and that's why we get a racemic mixture, even if we react at a CH bond on a stereocenter. And here's a picture of that flat radical. It has a mirror plane, and it can react from the top face or from the bottom face. Okay, so to summarize, what I'd like you to know is that fluorine is the most reactive halogenation reagent, but we're not going to really worry about that. We're just going to look at chlorinations and brominations. Iodine does not react because it's endothermic. Bromine is the least reactive halogen that we're going to study and the most selective. So tertiary CH bonds react much faster than secondary, which react much faster than primary, whereas fluorine is the most reactive and least selective, so you're going to get mixtures. You will also get mixtures from chlorination. I want you to be able to understand the stereochemistry of radical reactions and predict how many different stereoisomers are going to form in a particular radical reaction.